All right, let's open up to page 415. We have 3 more trig graphs to get through. I'm not sure if we'll be able to get all 3 of them done today, but we'll try. Okay, but we're not going to rush it. On page 415, we're going to start to take a look at the reciprocal trig graphs. Up to this point, we've already covered sine, cosine, and tangent. Now we're going to see what would happen if we were to flip some of those points on the graph, like flip or to find their reciprocals. So let's first try to figure out cosecant of theta. What is that the reciprocal of? Which trig function? Yeah? 1 over sine, okay, and if sine represents a y variable on the unit circle, we got to think about 1 over y when we go through filling out this table. So let's think about our unit circle. We'll just draw kind of a coordinate system to help us out. At the beginning spot on our unit circle on the right hand side, we have an ordered pair, 1, 0. So we need 1 over the y value. What would be 1 divided by 0? Yeah? Undefined. So what do you think is going on the graph? If you're in an undefined location, could we think of some possibilities? Yeah? It could be a vertical asymptote. It could also be, yeah? An open circle or a hole, yeah. So we just have some undefined discontinuity happening at that point. It's specifically a vertical asymptote in this case. Okay, we'll see what that looks like, but it could have also been a hole. Just because it's undefined doesn't mean it's an asymptote every single time. We have to be careful with that. All right, let's try pi over 4. That's the middle of the first quadrant. We have square root of 2 over 2. Good morning. Anything for the office today? I think we're good, honey. Thank you. Have a good day. All right. We need 1 divided by the y value. So let's see what that would look like. 1 divided by square root of 2 over 2. Instead of dividing by a fraction, we can bring it up and multiply by the reciprocal. So 1 times 2 over square root of 2. We don't want to square root in the bottom, so we can move it, multiply it on top and bottom. So change to a 2 on the bottom. 2's cancel, so we're left with the square root of 2. As a decimal, if we want to plot this, 1.414. All right, let's try pi over 2, the very top. Ordered pair 0, 1. We need 1 divided by the y value. So that'd be 1. Bless you. What about the next point, the middle of the second quadrant? Can we think about 1 over y? What would that look like? What do you think, Marie? Yeah? It's going to be another square root of 2. Yep. So the middle of the second quadrant has the same ordered pairs as the middle of the first quadrant. We just got to be careful what's positive or negative. So in the second quadrant, y is positive. That means we're going to have the same result as we did before. Pi, very left spot, -1, 0. 1 divided by 0. It's another undefined location. So vertical asymptote. 5 pi over 4, middle of the third quadrant. Y is negative in that spot, so we'll need a negative square root of 2. At the very bottom, ordered pair is 0, -1. 1 divided by y would be -1. 7 pi over 4, middle of the fourth quadrant. Y is negative, so negative square root of 2. And back to where we started, another undefined vertical asymptote. Yes?
When it's unified module hole.
It's not going to be a hole in this case. What, you just mean like in general? So when we, earlier this year, I wasn't here for this. Mr. C covered this with you guys. When you were talking about rational functions, like fractions, notice how the x minus 1s could cancel each other out. So x equals 1 would be a whole, because you can cancel that factor out. But x equals negative 4, since that factor doesn't cancel out, that would be a vertical asymptote. Okay? Good question. All right, let's go ahead and plot some of these points. Let's see what the cosecant graph looks like. So at 0, we need an asymptote. Pi over 4, we're a little bit less than 1.5. Pi over 2, we're at 1. 3 pi over 4, a little bit less than 1.5. And then at pi, another asymptote. Then it starts to get negative. So negative square root of 2, not quite negative 1.5. Then we have negative 1, not quite negative 0.5, and then another asymptote. So it might look weird when you're just plotting the information, but we have to use the characteristics to help us get a good visual picture, okay, of what this graph might look like. So we know we never cross or touch vertical asymptotes. So if we were to try to draw this graph from left to right, on the left-hand side, we'd have to be very close to the asymptote. We don't touch it or go past it. We're just close to it. But as we travel to the right, we're going to have to connect the dots. And on the right-hand side, we're kind of restricted by that asymptote again. So you're almost creating some type of a parabola shape, okay, between those asymptotes. The same thing's going to happen down here. This time we're just upside down. All right, so there's one cycle of a cosecant graph. I don't want you to draw this in, but if we were to repeat the pattern, notice how it would probably look like this. Okay, we could just keep repeating that cycle over and over and over again, and that would be our cosecant graph. We're not going to do that so we don't get too cluttered, okay, but just keep in mind that this would repeat itself. Let's see if we can figure out the period and the amplitude. All right, if this is one cycle, how wide is that cycle? What do you think, Marie? 2 pi. We start at 0, we end at 2 pi, so our period's 2 pi. Now the amplitude for these reciprocal graphs are a little different. When we talked about sine, okay, sine, just as a little refresher, started at the origin and we had that wave. When we talked about an amplitude, we've always measured from the baseline, okay, the middle of the graph, and we had to count up or down to the highest or lowest point. What's happening for these reciprocal ones is we still have a baseline, okay, in the middle of the graph, but instead of counting up or down to the highest or lowest point, we're going to count up or down to the vertex of those parabola shapes. So it's a little different of a measurement. It's still an amplitude, or by definition it's still an amplitude, but it's just a different way of measuring it. So from the baseline, notice how we have to count up 1 or down 1 to get to those vertex dots. So our amplitude would be 1. If we think about it, I hope this makes sense, because again, when we went over sine, the period for sine was 2 pi, and the amplitude for sine was 1. If cosecant is the reciprocal of sine, meaning they're related to each other, they should probably have the same characteristics. Notice how it's 2 pi and 1, just like sine was. Do we see that connection? Okay, let's see if we can kind of manipulate or stretch this graph a little bit. What if we were to multiply by 3 out front? What kind of change would that cause? Yeah.
A vertical stretch.
Vertical stretch by 3. All right, so we're going to see how that changes either the period, amplitude, maybe both. All right, so we're going to pull this graph up and down. We're not changing the width. Okay, we're just stretching it up and down. So if we're not changing the width, that means the asymptotes are going to stay right where they are. They're not getting wider or skinnier. Okay, asymptotes are staying. We want to change the heights though. So the two most easiest points to probably manipulate would be those vertex points. If this vertex has a height of 1 and we want to stretch it by 3, this one would move up to 3. Okay, it's starting at 1 times 3 would move it to 3. The bottom vertex has a height of -1, so if we triple that, it would be at -3. So we're going to keep the parabola shapes, okay, trapped between those asymptotes. But notice how we pulled or stretched the graph. All right, can we pick apart period and amplitude? How wide is our red section? Yeah? Still 2 pi, right? We did not change the width, so the period stayed the same. What about the amplitude? From the middle of your graph, how much do you have to count up or down to get to a vertex? Yeah, good, Marie? It would be 3, all right? The middle is still at 0 on that x-axis, and you got to count up 3 or down 3 to get to those vertex. So we'll say the amplitude's 3. Good job. All right, let's go ahead and try the next one. What if we multiply by 1/2 on the inside? How does that change our graph? Yeah?
It will stretch it horizontally by 2.
Horizontal stretch by 2. Remember, inside does the opposite of what you would think. I know it's a 1/2, but we actually multiply by 2. So let's see how that affects either the period or the amplitude or both. All right, so we're going to go back to the black graph, the original one that we start with, the parent function. We need to double all of these horizontal distances. Okay, we're going to make it wider. If we take a look at the first asymptote, that has an x value of 0. If we try to double 0, that's not going to go anywhere. So this first asymptote stays where it is. Let's see. Let's move on to the vertex on the black graph. That's probably an easy point to use. This vertex is at pi/2 on the x-axis. So if we double that pi/2 distance, this point would now land at pi. If we double pi/2, we land at pi. The next characteristic on the black graph was that middle asymptote, which was originally at pi. So if we double pi, it's now at 2 pi. Next characteristic on the black graph would probably be the bottom vertex. That was at 3 pi/2. If we double 3 pi/2, that would move to 3 pi. Because the 2's would cancel. We're just left with 3 pi. And the last asymptote was originally at 2 pi. And if we double that, we should be at 4 pi. All right, so we're just taking the one cycle, the one black graph, and if we stretch it, now notice how we'll have this very wide blue graph. So we still have the parabola shapes. They're just stretched out or wider. Can we identify period and amplitude? How wide is our blue graph? Yeah, 4 pi, good. If we double the length, we're doubling the period. If the original period was 2 pi, we double it, we get 4 pi. What about our amplitude of the blue graph? Yeah, it's still 1. Good, we didn't change the height. All right, let's try a practice one. Let's say we had, I don't know, we'll do 2 cosecant of 2 theta minus 1. Can we identify some transformations or changes? How it affects period or amplitude? What do you think, Marie? Yeah.
Is baseline will now be -1?
Baseline's -1. That's the middle of your graph. Good.
Yes.
What about the 2 out front and the 2 on the inside? Yeah.
The 2 on the inside, wouldn't it now be pi over 2? Because you have to multiply.
We got to multiply by what?
You would multiply it by 1/2.
By 1/2. Okay, so this is affecting your period. If your original period is 2 pi, and we have to multiply it by 1/2,
Oh, it would just be pi.
it would just be pi, right? So your new period is pi. So that original cycle, that black graph we had, instead of going all the way out to 2 pi, it's now only going to pi. So you have like really squished parabola shapes. Okay, they're kind of tight together. What about the 2 out front? How does that affect our graph? Yeah.
A vertical stretch by 2.
Vertical stretch by 2. All right, so this is affecting your amplitude. If your original amplitude is 1, we're going to stretch it by 2, aka times 2. So our new amplitude is 2. So that's telling us from the middle of our graph, which we now know is at -1, we have to count up to or down to get to those vertices. Okay? I want you to visualize this. We're not going to graph it exactly, but I want you to think about what this would look like. Okay? If our period is pi, we'll have an asymptote at 0, the last asymptote at pi, and the middle asymptote would now be at pi over 2, because we go from 0 to pi. Let's see, the middle of our graph we'll say is at -1. Really rough sketch here, guys. And we have to count up to or down to get our vertices. So if we count up to and down to, we'll have a dot and a dot, parabola, parabola. You see how quick that is after we have our transformations? All right, and we know the height of these dots. If we count up to from -1, we're at 1, and if we count down to from -1, we're at -3. Okay, really quick once you have the transformations. We're not going to do that on here because it would get very cluttered, but notice how it's still quick. Okay, let's go ahead and fill in the table on page 411 for all this cosecant information. Let's see, the domain is going to be a little tricky because we have asymptotes in there. That means we can be all real numbers, but x cannot equal certain values. We have to skip over those asymptotes. What was the period of our cosecant graph? How wide was our cycle? 2 pi. Good. We did have asymptotes, so we'll try to list where those were located. Okay, so taking a look on our black graph, let's see, we had one asymptote at 0, another asymptote at pi, and the last asymptote was at 2 pi. Let's go ahead and list those. 0, pi, 2 pi, and we could throw in the dot dot dots depending on how many cycles we wanted. So with this listing of vertical asymptotes, we're going to try to write a rule for our domain, okay, where every single vertical asymptote is located. We did this a little bit when we first introduced periodic functions. I know it's been a while, but we're going to try it again because we're going to see it a few more times with these graphs. What do you think, Marie?
Wouldn't it just equal pi n?
Okay, so your rule consists of 2 parts. Okay, the first part is some beginning asymptote that you want to write. You could write 0, pi, 2 pi, I don't care. You just got to pick one of those. Maybe we'll pick 0. The second part that Marie noticed is the pattern between the asymptotes. What do you have to add each time to get the next one? And notice how we have to add pi in our sequence. So we're going to add pi, but depending on how many times you want to add pi, we're going to throw in the variable n, so that represents the number of times. So for instance, if I want to add pi 3 times, we would have another asymptote at 3 pi. You see how it can continue the pattern. All right, so your rule has 2 parts, a beginning value and that pattern. Okay, we'll practice that a little bit more when we take a look at secant. What about the range of our graph? If you go back to our black one, if you were to drag your pencil low to high, where do you touch your graph? How far low can it go? What do you think, Tori?
Negative infinity to negative
Okay.
1.
And 1 to infinity. Perfect. All right. Negative infinity to negative 1 with a bracket. And 1 to infinity. We got to skip over the middle section where the baseline is located because we don't have any graph there. Notice how the range would change, though, if we were to vertically stretch our graph. Okay, let's take a look at the red one for a second. Notice how the red graph goes from negative infinity to negative 3, and then 3 to infinity. Okay, so the range would change if you stretch it. Do we have those characteristics down? Good to go? All right, let's go ahead and try another one. Very similar. We're going to try secant this time. That's 1 over cosine, which in terms of our unit circles, 1 over x. All right, starting with our table. 0 angle, look at our coordinate. 1 divided by 1 is 1. Next point, middle of the first quadrant. We need 1 over the square root of 2 over 2. From the last example, we simplified that to the square root of 2, which we can write as a decimal. Let's see, pi over 2 at the very top. We have 1 over 0, which is undefined. Bless you. 3 pi over 4, middle of the second quadrant. X is negative in the second quadrant, so we'll have a negative square root of 2. At pi, we need 1 over negative 1. 5 pi over 4, middle of the third quadrant. X is negative, so we'll have negative square root of 2. Bottom coordinate, 1 over 0, undefined. Seven pi over 4, middle of the fourth quadrant. X is positive there. And back to where we started, we'll be at 1. All right. Let's graph some of these points. 0, 1, not quite 1.5, asymptote. Then we get negative. Then another asymptote. And then we're positive again. All right, there's one cycle of secant. Now, if you were to fill in the dots, we would have a half of a parabola initially. We'd have a full negative parabola, and then a half of another positive one. That looks very strange. Okay, now it's up to you. We can keep it like that, or what if we continued the pattern on the right side and we erased the part before? You know what I mean by that? Instead of keeping it like this, if we continued the pattern, we would have another parabola and another asymptote. Do you guys want to erase the first part, or do you want to keep it the way it was originally graphed? It's up to you. Do we have a preference? No? All right, maybe we'll keep it, just because that's what the table looks like. Okay, but realize it would look exactly the same as the previous one. It's just a little bit different because when we did cosecant, we had an asymptote at 0, and now notice we have a vertex at 0. There's a slight difference between the two. They still have the same shape, they're just located at a different spot. All right, let's see if we can identify amplitude and period. How wide is that one cycle? From beginning point to ending point, looks like 2 pi. Hopefully that makes sense because cosine has a period of 2 pi. And our amplitude, if you were to draw the middle of your graph, looks like you got to count up 1 or down 1 to get to a vertex. So our amplitude's 1. All right, let's try some stretches. Multiplying by 3 on the outside, that's our vertical stretch by 3. All right, so we're just changing the heights, we're not changing the widths. That means the asymptotes are going to stay where they are. We got to multiply all the vertices by 3. So this first vertex now moved to 3. The middle vertex down to -3, and the last vertex up to 3. So if we keep the same shapes, we'll get our stretched graph. This should be up one more. There we go. What about period and amplitude for that red graph? Yeah. Perfect. We didn't change the width, so the period stayed the same. Amplitude from the baseline at the middle, you got to count up 3 or down 3 to get to a vertex. Perfect. Let's try our horizontal stretch by 2. Okay, so we're going to double all of our x distances, or we're going to double our width. Let's see. On the black graph, the first dot we have has an x value of 0. If you try to double 0, it's not going to move. It's going to stay right where it is. The next characteristic on the black graph would probably be the asymptote, something easy to work with. That's at pi over 2. If we double pi over 2, we're now located at pi. The next easiest characteristic I would say would be the bottom vertex on the black graph, and that's at pi. So if we double pi, that'll move to 2 pi. The next black characteristic is the asymptote at 3 pi over 2. If we double that, we're at 3 pi. And our last characteristic would be the last vertex on the black graph. That's at 2 pi. If we double it, we're at 4 pi. So we're going to keep the same shape trapped between the asymptotes. Notice how we've horizontally stretched the black graph. Okay, we made it wider. Our parabolas are larger horizontally. Can we determine period and amplitude of our blue graph? How wide is our blue graph? Yeah?
Period
4 pi, good. And amplitude? Yeah, still 1. We did not change the height. Perfect. All right, let's practice. We have 4 secant of 1/3 theta plus 3. We're not going to graph it. Okay, we're just going to talk about some transformations. What can we identify about that graph? Yeah? Baseline is 3. Good. Everything moved up 3. So that's where your middle is. What about the 4 or the 1/3 inside? What do you think, Marie? Go ahead.
Because the period is 2, would it should be 2 pi by 3?
Okay, so this is your horizontal stretch by 3. Remember, it's the opposite of what you would think. So that's going to affect our period, okay, how wide our graph or cycle is. So the original period for secant is 2 pi. If we're going to stretch it by 3, our new period is 6 pi. It's a pretty wide graph, a pretty wide cycle. All right, what about the 4 out front? Yeah?
That'll be a vertical stretch by 4, so you multiply the amplitude by 4.
There you go. So that's going to affect your amplitude. Your original amplitude is 1, vertically stretched by 4. We'll give you 4. All right, so if we were to think about it, the middle of the graph is at 3. We would have to count up 4 units and down 4 units to get the vertices on those parabolas. All right, so a little visual here. Middle of the graph is at 3. We got to count up 4 and down 4 to get our parabola shapes. So notice how we could figure out the heights of those parabolas. This one would be 7, this one would be -1. Okay, from the baseline or the middle of your graph. And then the width of this would be 6 pi. So from beginning to end, okay, that whole distance is 6 pi units. Fairly wide. I think we're doing really good, guys. Awesome. Let's end it with our characteristics for secant. Very similar to cosecant. We had some asymptotes, so we're going to have to write a rule. Let's see, our period was 2 pi. Let's maybe start with the asymptotes. If we look at the black graph, we had asymptotes at pi over 2 and 3 pi over 2. Those were the only ones we listed in our cycle, but we know there are more, ... So can we write a rule for our domain? You gotta think about the 2 things you need for your rule. Bless you. Let's see, the first part of your rule, you gotta just pick a number or asymptote to start with. Maybe we'll do pi over 2. And then we have to add the pattern. So what do you have to add each time to get from one asymptote to the next? Maybe think about it in terms of fractions. This is 1 over 2 and then 3 over 2. So you're going from 1/2 to 1.5. What do you have to add from 1.5 or from 1/2 to get to 1.5? Yep. Pi, or just 1, right? 1 pi. All right, so that's what we have to add each time. That's our pattern, and then we'll put an n on it to represent the number of times we want to add that pattern. Looks good. Last but not least, we need range. So on our black graph, from low to high, Lowest we go negative infinity, up to -1. We skip over the middle section where the baseline is, and then we touch it again back at 1, all the way up towards infinity. So it looks like it's the same exact range as cosecant. But remember, the range would change if you vertically stretch it. We doing okay? All right, bell's gonna ring in a little bit. On Monday, we're gonna pick up with our last one. Okay, we have one more graph of cotangent to do, and then we're gonna take a look at manipulating some trig functions. We're gonna shy away from graphs a little bit. All right, you guys have a good weekend.